The challenge of building micro machines and micro robots that can swim is that there are no parts or motors that are sufficiently small. Therefore, whatever is built must be simple. And the simplest mechanism possible is just something that expands and contracts, or something that opens and closes like a clamshell. Unfortunately, at very small length scales, this flapping motion cannot be used for swimming in water, because the physics for swimming at small scales, in the low Reynolds number regime, are different from those that we know and experience when we swim. The law which describes this restriction is known as the scallop theorem, due to Purcell. It has been known for more than 30 years and teaches us that a simple reciprocal motion will not result in any net displacement at low Reynolds numbers. According to the scallop theorem, the microscallop is not able to move in water. However, there are fluids other than water that have different properties, so-called non-Newtonian fluids. Non-Newtonian fluids include most of the biological fluids one finds in the human body, such as blood, saliva, the vitreous in the eye, and the synovial fluid in the joints. Taking advantage of their non-Newtonian properties will help us to circumvent the scallop theorem. Here's the microswimmer that we built in the shape of a scallop. The width of the scallop is about 300 microns. It is made by first 3D printing a hard mold and then micromolding the scallop shell with soft polymer material. The opening and closing of the scallop is controlled by an external magnetic field, which allows precise modulation of the opening and closing speeds. The viscosity of non-Newtonian fluids depends on their shear rate, or in other words, it depends on the speed of movement in the fluid. When hyaluronic acid is placed in a rheometer between two moving plates, one can see that its viscosity is not constant. It is a shear thinning fluid, which means that it has a higher viscosity and thus higher resistance at low speeds, and a lower resistance at high speeds. It is the shear sensitive behavior that allows our microscallop to swim in non-Newtonian fluids. Now, instead of using a rheometer to change the fluid property, we're going to use the shells of the scallop itself to change the fluid viscosity in the area around it. To explain our scallop's motion, let's divide the stroke into two phases, a rapid closing phase and a slow opening phase. In this case, we're using a shear thickening fluid, so high shear rates result in high viscosities. During the closing phase, the speed of fluid between the two shells is very large, which leads to a high viscosity between the shells. But the viscosity in front of the head of the scallop is relatively low, so we have a net forward propulsion. Now, during the opening phase, which is slow, the viscosity is relatively low on both sides, and the scallop is sucked back as the shells open. The reciprocal nature of the stroke means that the scallop moves forwards during the closing phase and backwards during the opening phase. But because of the shear thickening property of the fluid, it moves forwards more during the forward stroke than it moves backwards during the backward stroke. The net result is that over many cycles, our microscallop moves forward. This is great news because now we can use really simple actuation schemes, like expansion and contraction, or opening and closing, to build swimming micro-robots that can move through tissue and biomedically relevant fluids.